sorry. Then I try to cover inversion first. So frobenius, first to compute the inversion of the extension field, we need to have a frobenius mapping first. So if you have a prime field P and frobenius mapping pi is defined like this. So phi of A is become A to the P. And sometimes we call this like frobenius endomorphism because the domain and what is the opposite of domain? Inversion domain and the area that the function maps is same. What is it called? Domain and codomain are same. That's why, we called it also at the same time endomorphism. And the interesting part of the Frobenius mapping has is like, so if A is composed of like A sub I times x to the I, some of this, if you actually compute parts of this, the interesting is like the thing that, so only this one is remaining and the rest of the terms are disappeared. It's because the intermediate term, like P times, for example, let's see, let's give an example. A0 plus A1I x to the square is with something like A0 square, A1 square, x square, and 2 times A0 and A1, right?
Mm-hmm.
Because this characteristic of the field is P, which means if you add this field P times, it will become 0. And also if you, and it works for the another powers. For example, if you do the cubic, A0, 3, A1, 3x, 3x, 0 times square A1 and 3A0, A1 square. This part also has a 3 coefficient because the characteristic of the field in
Can
this
you map
is
equation it? Yeah, I think I can see it.
Yeah. So if the characteristic is field is P, so for example, like I think I have a mistake though, but if you have a if your field, if the characteristic of the field is 3 and all these coefficient, all the terms that have 3 will be disappeared, which means you only will have a get this part is only. So for example, so A0 plus A1 to the Px to the P A2 P to P X to 2P, something like that. Only this part is remaining. Then the question for this is like that, how do we compute this efficiently? That's another interesting point. And the purpose of all of this is like to compute inverse efficiently for extension field. So for example, if the extension is defined by like, for simplicity, we always, most of case extension field is defined over this irreducible polynomial. X to the k is equal to xi or beta or something like that. And for simplicity, we assume that this extension field is construct based on the prime field. And we also assume that this prime field is t minus 1 is divisible by k for simplicity. And in most cases, this is true also. Then every xip, for first, let's set q is set to p minus 1 over k. And then ip can be rewrite as something like this. And if you distribute, we will get this form. And if we move k to the left side, then we will get the xk to the iq and xi. And because x to the k is xi, so we can compute this efficiently using this expression, simple expression.
So is P always one modulo 1 by K?
Yeah, most case, for example,
Okay.
if case 4 quartic in if it is quartic extension fit, the 2 of this t is like 2 to 2. Or for example, if you use QB, if case 3, then trace is divisible by 3.
I meant the P. So I see. So it's we're only considering P when P is mod 1 by K, right?
Yeah. But in most cases, it's true. Like 2, 3, 4, 5, kind of. Yeah, it's very easy to construct prime fit with this assumption.
Okay.
Then the frobenius mapping of A can be computed. Yeah, if you unfold this, then will become this and this for based on this computation. And if you unfold all the terms like that, then if you want to compute frobenius mapping efficiently, then what you need is like you need to compute all these terms as a vector as a precomputation. So if you have all these at precomputation days, then you can compute the frobenius mapping very efficiently. And the fact that if you frobenius mapping k times, you will go back to A because it has a p minus 1 over k. If you if you compute this to the k, then you will get the xi to the p minus 1, which is like xi at 1. Right? According to the Fermat theorem.
So we just need K multiplications? No,
K
minus 1.
exponentiation. Yeah, because
we already computed the psi exponents, so we just need to compute a1 psi, a2 psi, a2 powers of psi, kind of like we just need that scalar multiplication, no?
I don't understand your question.
So to compute,
so what we compute is for this is for like frobenius mapping of at the exponent of 1, right?
Okay. So you want
The second one is like something like this p to the square, p to the square, something like this. This is the coefficient needed for like phi square. Because if you remember what the frobenius mapping does is like it will powers a to the p. So if you do 2 times, it will become a to the p square. If you do 3 times, it will become a to the p to the 3. So it will become, you need to compute something like xi to the p minus 1 over k, xi to the p square minus 1 over k, or something like that, up to k times.
But they will also be pre-computed, right?
Yes.
Okay.
All of them are pre-computed. And the interesting property that the frobenius mapping has is like norm. So norm is defined by this. So norm of A, where A is extension field, it will be defined like that. So you will multiply all of the frobenius mapping that values that have. So this technically will be phi to the 0 of a, phi 1 of a, phi 2 to the of a, phi to the k minus 1 of a. This is norm. And the interesting thing is, like, I will explain later soon, prove it to you soon, but this, no matter what A is, it will always prime field.
Prime field?
Yeah, it will always become a prime field again, even if A is extension field. So the reason why is because, so yeah, to prove it, first, yeah, if you have a norm, let's do the frobenius mapping again on top of this norm again. Then phi to this term, phi to this one, and then phi can come inside these parentheses, and then we get this, which means we will get the phi 1 of a, because we will apply phi to the a. So phi 1 of a, phi 2 to the of a, phi to the k minus 1 of a, phi k of a. And since phi 2 to the k of a is a, which means phi of n of a is n of a. And the in order for this condition to be met, that which means if you compute a to the p, it become a. The order of multiplication is p minus 1, and the only case that satisfy this condition is prime field, because extension field, the multiplication orders, we get the like p to the k minus 1. So the fact that the multiplication order of p minus 1 implies that this is prime field. So norm, if you compute norm is always prime field. Okay, then, so yeah, the reason why I explained this is because I want to explain how to compute inverse of fp to the k. So to compute the inversion, let's first define R like that. So R is equal to p to the k minus 1 over p minus 1, which is sum of all these parts of p up to p to the k minus 1. And then we can rewrite inverse of x using R like that. X inverse is x to the I minus 1 times x minus R. And this exponent I minus 1 can be expressed as sum of parts of p, because R is this, so I minus 1 is like sum of from p to the k minus 1. And x to the I minus 1 is basically the product of phi of x to the phi to the k minus 1 of x. Then next is like, now, so we compute the left part of this, and we need to compute the right part of the right hand side. And x to the r is basically the product between x times x I minus 1. And we compute this already here. So we just need to compute, multiply x again. But if you remember, this is the, if you multiply x here, then this is a norm. Then which means this is a prime field. and we need to compute the inverse of this x to the r. Typically, inverse operation is very expensive, and if it is extension field, which is could be expensive, but we know that this will become this will become a prime field.
Yeah.
Yes. So we get this, and we only compute the inverse of this prime field only, which means we just only need a constant term of this polynomial. So I use this notation for constant term. So this is the way to get to the right part of this. Yeah, then all the terms are computed, and that's how the inverse of extension field is computed. And this is a principle that is used by, I guess, quartic extension field, not only quartic extension field, but also I didn't get noticed, but yeah, I found that the cubic extension field inversion is also using this algorithm. Yeah, that's all. I kind of shame that stuck in the middle of Tunku. I prepare again and explain soon.
So do you know if Jungkook is always faster